All right, how's everybody doing today? Good, bad? Is the volume okay and back? Good. All right. So, hi everybody. How was your weekend? I don't care. Any questions on the homework? Have you all gotten started yet? Yes, sir. No, on 2 and 3, I want you to make one algorithm that chooses between the pizzas. That chooses between one algorithm. So you might have an algorithm that computes the cost per unit area for each, but just doing one for each isn't good. You have to do the part where you actually decide which is superior. Okay? Yes, sir. Sorry, one sec. Let me close the door. Remember I said earlier I don't always hear very well. You might have to speak up a little bit, but there was background noise. Go ahead. Say again. Input, output, start, stop, decision. Yeah. Decision is you have a choice to decide between two things. So you can say decide A is bigger than B, decide round pizza cost per unit area is less than, and then underneath you put a couple of other statements. You'll see that today. I'll show you an example on the board for sure today. Yes? Yeah, use decision. Decision is essentially the language for an if statement in this. Yes, sir. Great. Sure. I mean, this isn't like a formal language that the compiler is going to yell at you if you get it wrong. It's just for you to think about your algorithm and to communicate to me and the TAs that you have thought about it and have something. So there's not like a strict thing that if you don't do it exactly our way, we're going to laugh at you and throw you out of the class. That comes later. Okay. So. Actually, that never comes, just in case you weren't aware I was joking. Other questions about the homework? Yeah? Diameter. Other questions? Who tried Lightbot? Who played all the way through? Isn't it fun? That's everything you're going to learn in the entire semester. Okay? That's kind of what we're doing. The one thing Lightbot doesn't have is a decision, right? You will learn about functions and procedures later on. Lightbot doesn't have a decision, but it has pretty much everything else you need. Plus, it's fun. So that's all the concepts. I make my kids play that. Actually, I make it a huge reward to them, and then they get really excited to play it, which is even better. So. Other questions about the homework? Anything? Yes? Sure. Anything. You can turn it in as a PDF file, which means you can write it as a Word document. I don't accept Word documents as a submission, though. So you can convert it to a PDF. You can write it in hand and take a picture and turn it into a PDF. As long as it's a PDF file and it's legible, I don't really care what it is. Other questions? Going once, twice. All right, so every class I kind of like to talk over the high points from last time just to reinforce things. Reinforcement through repetition is good, right? Reinforcement through repetition is good. Last time we talked about algorithms. What is an algorithm? A series of steps used to perform a task. Excellent. In fact, would you like some candy? Yeah? Awesome. Because like you as a class are really not into the candy as much as my last classes. I'm a little worried I'm going to have to eat it all myself. So, all right. So that's an algorithm. And what is a program then? Because we talked about programs. Show of hands. Anybody want to take a shot? Yes? And? That's half of it. Yes? Yes, both computers and humans are important in programs, okay? A program is an algorithm expressed in a form a computer can execute because computers are very powerful and do stuff very, very fast, and humans can understand. The humans can understand part is very important. Other people will have to look at your code and understand it. Okay? So we talked about computers. They're stupid, but they are stupid very, very fast, unimaginably fast. So here's what we're going to talk about today. We're going to talk about how computers do this, like how they are stupid so very, very fast. And the reason we need to understand this is because the way we program is directly influenced by the structure of the computer, right? When we talked about algorithms and giving things, we said we have to give algorithms using instructions that whatever entity is running the algorithm can understand, right? And you talked about me walking to the car barn versus Superman flying there. The computer is limited in what it can do by its structure. So we're going to look at its structure. So let's start, and we're going to take a deep and detailed examination of how computers work. All right? So let's start with asking this question. What is a computer? Well, this is what computers used to be. Computer at one point wasn't an object. It was actually a profession. And here you see a room full of computers sitting to do work. Here's another view of the same room, the computing division, computing section, and all those people, mostly women, were computers. And they just sat and did math all day. This is actually pretty advanced. They all have mechanical adding machines. Before that, computers just used pencil and paper and their brain. And they got very good at it. They could add much, much faster than you all could, judging by how long it took to do the math addition versus the computer quiz. All right, so anyway, that was an old computer when it's profession. Now we're talking about modern computers. So let me give you a very detailed diagram. There is a computer. Okay, I lied. All right, this isn't really what a computer looks like, right? A computer is not just a rectangle. The picture I showed you was a rectangle, not a computer. So here's the thing. I'm going to lie to you very often in this class. I'm going to lie to you a lot. The reason I'm going to lie to you is because what we're learning is complex. And I cannot just dump all the complexity on you at once without breaking your will to live. All right? I just can't do it. So what I'm going to do is I'm going to lie to you sometimes, and I'm going to lie to you to hide complexity. I'm just going to give you something that is simple enough for you to work with at a particular time to solve a particular problem, and then later, either in this class or if you continue in computer science, you will get more detail, and my lie will become apparent. Right? Now, one thing I promise you is I'm never going to lie to you and then grade you on what the truth is. Right? I'm not going to lie to you and say computer's a rectangle, and on the exam say, what is a computer? And you say it's a rectangle, and I go, well, that's clearly wrong, and take points off for that. I won't do that to you. All right? I will only test you on the lies. Okay? So, just so you know that and feel comfortable. Everybody comfortable with that? So it's just kind of necessary because this stuff is very complex, and if I tell you all the complexity at once, you would actually be unhappy. All right, so here's our computer. This probably isn't detailed enough for us, so let's make this a little bit more detailed. So if we open up a computer and we look inside and we look at what's outside, we find a few major components. The major components that we're interested in are the CPU, the RAM, the disk, and we have a keyboard and screen as well. Right? Is there really more stuff inside the computer than that? Anybody ever opened up the computer and looked inside? Anybody built their own computer yet? It's kind of fun, isn't it? So if you want a really good computer, the way to do it is build it yourself. It's surprisingly easy. It doesn't come with a warranty, though. That's the sad part. Okay? So here's what's in our computer: CPU, RAM, disk, keyboard, and screen, and they're all connected by something called the bus. And the bus is the part of the computer that sends signals and allows communication between the disk, the CPU, and the RAM. All right, so each one of these parts, the CPU is the central processing unit. The CPU is the part that does all the math, right? Said computers can do math. They do math very, very fast. The CPU is the part that does all of the math. Now, one of the things about the CPU is that most of its circuitry is set to do math, right? And so, yes? That was weird. Okay, so most of its circuitry is set up to do math. It's expensive to make CPUs. And so they put all the circuitry that does math in there. The problem is when we do math, we need to do math on numbers. And we need a place to hold all the numbers. So we also have RAM. RAM is memory. It is the part that holds all the numbers that we perform math with. Okay? CPU has all the circuitry to do math. RAM has just lots and lots of circuitry to store numbers. How do the numbers get from the RAM to the CPU? They take the bus. Exactly. Okay? They take the bus. Pardon? No, it's not a lie. It's a simplification, but not a lie. In a real computer, you will have multiple buses. Different parts of the CPU will be connected to different parts of memory. There's additional microprocessors in there between the CPU and memory that do other stuff. But for our purposes, that's all we need right now. And for our model of programming during the semester, this is exactly what we need. We don't need anything more complex than this. And it's actually a pretty reasonable simplification. So, okay? Okay, RAM and CPU, what do they run on? What? Nope. What do RAM and CPU use to compute, to operate with? What physical phenomena? Electricity, right? They run on electricity. Now, since the CPU and RAM, the way they're constructed now, run on electricity, we need one other part in our computer. And the reason we need one other part is, does the electricity always stay? Do you have a permanent source of electricity? You do not. How many of you ever had the computer, you've stepped on the switch on the power cord or pulled it out or had a sibling do something? Right? For a while, my 2-year-old son thought it was hilarious to sneak up and turn off the computer while I was working on it. Because instead of being boring inert daddy, I'd be very energetic, flailing daddy. And that was much, much more fun. So since these things run on electricity, electricity sometimes goes away, we have a disk, okay? When the RAM and the CPU lose electricity, they are no longer able to remember data. It goes away. That's also sort of a lie, but we don't care. It's close enough for our things. And disks actually work on a more permanent basis. Okay. These days we have several kinds of disks, but the unifying feature of the disk is that when you stick something on it, it doesn't go away if you lose electricity. So it's our permanent non-volatile storage. All right, questions so far? Yeah. Yeah, absolutely. No, the disk, so really don't be shy. That's an excellent question. And I wish I should have brought a computer with me to like show you what's in there, but if you ever open up the case, you'll see there's like a green circuit board. And the circuit board typically has a socket that there's a big thing in. Most computers, this thing has like fins or a fan sitting on top because the CPU generates a lot of heat as part of its computations. They have something to kill that. The RAM normally come on sticks that have little modules mounted on them, and they jump into a little slot. And then there's different forms of disks. Like inside your laptop these days, you have what's called a solid-state drive. It looks kind of like a memory stick. It's like a green circuit board with some modules, but the modules on that work differently than the RAM. They are much slower, but they remember things. Or you might find like a little silvered sealed like box like this. In there, there's actually a disk that's literally a disk. It's round, it spins, there's a head on it. If you've ever seen like a record player, God, record players are normal to me, but you know, you all didn't grow up with them, and there's a little head that moves across the surface of the disk. So disks were originally literally a disk that spins, they have a magnetic surface, and they have a little head that can read and write magnetic dots. And if you want to come by my office sometime, I have a whole bunch of this stuff. We can open up a computer, I'll show you what's in there. I'd be happy to do that, okay? Okay, so here's the thing about electricity. It's easy to tell if it's on or off. It is harder to tell how strong it is. So if I came up to you and shocked you with an electrical shock, would you know if you were shocked or not? If I shocked you with like 100 volts versus 200 volts, would you be able to go, that shock was, 100 volts? Probably not as well. And same thing happens inside RAM in the computer. So what ends up happening is it's easy to tell if there's electricity on or off. It's harder to tell the level, so we just do the lazy thing. The lazy thing is just figure out if electricity is on or off. Because of that, we only have two things, right? You can tell if the electricity is on, you can tell if the electricity is off. So we have binary numbers. Anybody want to tell me what binary numbers are? Yeah? Exactly. Binary numbers, all we have is zeros and ones. All we have is zeros and ones. So any number that we work with, and remember the computer is doing lots of math, has to be made only of zeros and ones. That's it. So zeros and ones. Now we call these Boolean values as well. A Boolean value is 0, which is false or off. And we have 1, which is true or on. We have two kinds of digits, off or on. Now, that's not what we're used to doing, right? Most of us, when we do math, we don't do math with just two digits. How many digits do we use? 10, right? 0 through 9. Instead of just 0 and 1, we have 0 through 9. So our numbers, when we're doing base 10, look like this, right? This should be pretty familiar to you all from, I don't know, what grade did you learn this in? 10 to the 0 is what? 1. So you might have some 1s in this column. 10 to the first is 10. You might have some 10s. And these digits tell us how many we have. 10 to the second is 100. 10 to the third is 1,000. 10 to the fourth is 10,000. 10 to the fifth is 100,000. So if we have 800,000s, 3 10,000s, 9 1,000s, 0 100s, 4 10s, and 7 1s, we can add all these up column by column, and we get this number 839,047. Everybody good with this? This is just pretty much what's going on. Okay, how many of you are with me? Show of hands. How many of you are against me? I had you picked out for that early on, so, okay. All right, you got this though? Okay, good. Okay, so this is base 10. So base 2, it works exactly the same way, except instead of powers of 10 for each digit, we have powers of 2 for each digit. And the powers of 2 go, 2 to the 0 is 1, 2 to the 1 is 2, 2 to the 2 is 4, 8, 16, 32, 64, 128, 256, 512, 1024, 2096, 2048, 4096, right? Do you want me to keep going? So when you're a computer geek, you end up learning the powers of 2. Because they're very important, because each one of these places is a power of 2. 1, 2, 4, 8, 16, 32, 64, 128, 256, 512, 1024, 2048, 4096, 16,232, 65,535, give or take a little bit there. Damn. Okay, I skipped 8192. Thank you. Right? But powers of 2, they go all the way out there. The way we figure out what a number is in base 2, same way as base 10. Are there any 2s? Are there any 4s? Are there any 8, 16, 32? There's 0 1s, there's 1 2, 0 4s, 1 8, 1 16, and if you add them all up, that number represents 26. The numbers we're representing with binary and decimal are the same. We're just representing them in different ways. Which is going to have more digits to represent the same number? Binary will, right? Because each one of these places only holds fewer values. So the numbers are not necessarily as compact. Everybody kind of good with this? We're going to do a little more of this. All right. This leads to the saying, there are 10 types of people in the world, those who can count in binary and those who can't. What is 10 in binary? It's actually 2, right? So when you're seniors, this will be very funny to you. I promise you, okay? And those of you who show up on my operating systems class 4 years from now, on the last day, I will make this joke, and I will see if you laugh then. Don't think I won't. I did it to my operating systems class this year. All right, so we can represent the same numbers, but it takes more digits. Okay? So binary numbers have their own terms. When we talk about binary numbers, we have terms for the pieces of the number and the structure of the number depending on how big it gets. Each binary digit is called a bit. A bit is a 0 or a 1. So each binary digit is called a bit. Computers work on bits. 8 bits is called a byte, B-Y-T-E, sometimes referred to as an octet. Okay? 1 digit is a, 8 digits is a, which leads us to this very natural conclusion, a hobbit and a hobbite, being 8 hobbits. Come on, that's pretty good. All right. 4 bits or half a byte is called a nibble. All right? Seriously, I'm not lying. For real. 1 bit is a bit. 8 bits is a byte. Half a byte or 4 bits is a nibble. I don't know why you're all laughing. It's true. The Hobbit thing was a joke, but okay. Okay. What? All right, what's one binary digit? What is 8 binary digits? What are 4 binary digits? Absolutely. No joking, I'm dead serious. Everybody got that? All right. We can also refer to a word, and a word is the size of the chunk of information that the CPU works with. It turns out that when you're building a CPU, it is easiest to always make it deal with like the same chunk of binary digits at the same time. Always, okay? If sometimes you're dealing with 1 bit and sometimes you're dealing with 128, it gets really, really complicated. So instead, the circuitry works on what's a word, which is the number of binary digits the CPU uses for any operation. Nowadays, for most of our computers, the word, that is the chunk of information that the CPU works on at any given time, is typically 64 bits. You can find some older things that have 32 bits, but just for practical purposes, we can say 64 bits is common. 64 bits is how many bytes? 8. So CPU works in 64-bit chunks. The CPU works in 8-byte chunks of information. Everybody happy so far? When we talk about the computer memory and the storage, we measure it in bytes. How many bits in a byte? How many bits in a nibble? All right, good. How big is the word in a CPU? 64 bits or 8 bytes typically, okay? So the memory and storage capacity is measured in bytes. How many bytes might we have in memory? A lot. Like how many is a lot? 100? Billions. We might have billions of bytes. How many in a disk? Trillions, right? So we have lots and lots and lots of these things. Billions or trillions. My server in my office has 256 gigabytes of RAM and 72 terabytes of disk. Okay? So it has just lots and lots of stuff. So when we have things that are millions and billions, we have to be able to talk about these numbers somehow. Right? We have to have some way of just, instead of saying 18 billion trillion numbers, we have things. So what we have is we have prefixes. And I heard some people shout out a few of them already. So when we're working on these with prefixes, we're going to work with them. And so what I'll talk about first is decimal prefixes, which are base 10. If you have 1,000 bytes, you have a kilobyte. The prefix is kilo for 1,000. If you have 1,000 bytes, or 1,000 squared bytes, or 1,000,000 bytes, you have a megabyte. If you have 1,000, or 1,000 cubed bytes, you have a gigabyte. If you have 1,000 to the 4th bytes, or 1,000,000,000,000 bytes, you have a terabyte. Everybody familiar with these things? Probably heard these terms before. Oh, one other thing. You all realize that I'm like recording these things and putting them online, right? Did you all see that the last lecture is up? So if you're taking notes and I'm going too fast, you can always drop back in and see, hopefully, when the recording works. Okay, just like we have these things for decimal prefixes, we also have binary prefixes. Now, the binary prefixes are something that computer scientists use because they are more precise. They're not often used, at least not correctly, in the real world. But we have similar things. 2 to the 10th bytes, which is 2 to the power of 10, is 1,024. It's slightly bigger than a kilobyte. It's called a kibibyte. Notice that the second sound here is B for binary, kibibyte, 1,024 bytes. 2 to the 20th bytes, which is roughly about 1,000,000. I don't remember the exact number off the top of my head. It's more, is a mebibyte. 2 to the 30 bytes is roughly 1,000,000,000. It's actually bigger by, I think, like 3%, is a gigabyte. And 2 to the 40th bytes, which is, again, 3 or 4% higher than a terabyte, is a tebibyte. Now, most of the time when you go to buy a computer or buy storage, they will measure the capacity in decimal bytes because it sounds a little bit better, right? A kilobyte is smaller than a kibibyte. So if you say you have a whole bunch of megabytes, you have more megabytes than you have mebibytes. But if you've ever taken a disk and formatted it with the operating system, you can take a terabyte disk, you format it with the operating system. When it comes out, it'll tell you it's like 950 gigabytes, give or take. And it's because your computer might be measuring in these binary units instead, so things don't always work out. Okay, I've been talking for 25 minutes. Who would like a 1-minute stand up and place break? Ready, set, go. All right, welcome back. How was your break? Do you feel better? Okay, so binary and decimal numbers actually represent the same numbers, right? There is some number that we can have in base 10, and we can have the same number in base 2, and it represents the same quantity. And if I were a math professor, I'm sure I could tell you some sort of formal proof of that, but I'm not, so I just won't. So one of the things that it helps to be able to do as a computer scientist on occasion is to convert numbers from one base to another. Okay? So let's talk about how to do this. So here is how you can convert 13 to binary. Okay? The official way to do this, and I think the way the book tells you to do this, is through what's called repeated division. Okay? So we take the number that we want to convert, in this case 13, shown there in purple, and we divide it by 2. What's 13 divided by 2? All right, we're not dealing with decimal points. What's 13 divided by 2? And how many are left over? So we write that out. 16 divided by 2 is 6, and we write the remainder as 1. We then know that we take this 6, put it down here, divide by 2. What's 6 divided by 2? Remainder. What's 6 divided by, the remainder of 6 divided by 2? 0. 3 goes in evenly. 3 divided by 2 is 1 with a remainder of 1 divided by 2 is 0 because 1, 2 doesn't go into 1, and there's a remainder of 1. Right? So that's how the book tells you to do it. And then when you're done with that, you know what the number is by reading these things backwards. So if you then go back up this and go 1, 1, 0, 1, you get 13. Everybody with me? Do that kind of fast? Yeah? Yeah. 13 divided by 2 is 6, remainder 1, put the 6 over here, divide it by 2, remainder 0, put the 3 over there, just like that. All right? That's the way the book tells you to do it. Now we can prove this works really fast by doing the opposite conversion, right? Given a binary number that's 1101 in binary, what we just have to do is figure out the number in each position, like what the value is in each position, just like we would do for ones, tens, hundreds, thousands, except here we have 1, 2, 4, 8. So we have 1, 8, we have 1, 4, we have 0, 2s, and we have 1, 1. If you add that all up, you get what? 13. Now, let me show you quickly on the board. That's the book way that I'm supposed to teach you. Let me show you quickly on the board how I do binary conversion. Okay? We'll flip up this light for a second. Somebody give me a number between 1 and 127. 126. All right. So here's what I do. You give me the number 126. Here's what I'm going to do. I'm going to write down all the powers of 2 that I know pretty well. Right? 1, 2, 4, 8, 16, 32, 64, 128. And I'm going to write them until the number gets bigger than the number I was given. Is 128 bigger than the number 126? Yes, indeed it is. So I know there are going to be no 128s. Is there going to be a 64? Does 64 fit into 126? It does. So I do 64, what's 64 minus 126 is 52, is that right? 62? Let's see, I get 30, yep, 62. So now I have 62 left. Does 32 fit into 62? Yes. So I put a 32 there, I take 32 out of that. I have 30 left. Does 16 fit into 30? It does. I take 16 out of this. I have 14 left. Does 8 fit into 14? Yes, it does. I take out 8. I have 6 left. I put one up there. Does 4 fit into 6? Yes, it does. I take 4 out of this. Put a mark up there. Does 2 fit into... Wait a minute. I subtracted wrong. There's 2 left. Does 2 fit into 2? Yes, it does. I have 0 left, so I put a mark there. Does 1 fit into 0? It does not. So 126 is going to be this number. 11110. 6 ones and a 0. Now I did that on the board. When I'm having a good day and I've slept, I can actually do this in my head for reasonable values of numbers. Okay? That's why you know the powers of 2. So you can do either the repeated division that I showed you, or you can just literally go from numbers, powers of 2 that are higher, and work your way down and just subtract out of the number. And each time you subtract a power of 2, you know that that power of 2 is present in the binary number. Yeah? So, all right, so the question is the first 0 included? The answer is not necessarily. You don't have to. I just normally, in my head, I just wanted to show you the step where I thought of the binary number that was actually bigger than the last one, and so I put that up there to make it clear. The other thing is that oftentimes when you write down binary numbers, we write them down in nibbles. So I always try to make my binary numbers have sets of 4, and including that one gives me a set of 4. Okay. Yes, sir? Yep. This is just like you read powers of 10, right? You'd be like 1, 1, 1, 1, 1, 1, 0, and I put the leading 0 in front. You can put as many leading zeros in front, it doesn't change the value, right? So, like if I gave you the number 100, it would be 100, but if I gave you 0, 100, it would be 0,000, 100, it would be just the same. Yep, yep, as many leading zeros as you want, doesn't matter. All right, everybody think they can do this? Right, we'll do a little practice on this in a second. Okay, sometimes when we're working with numbers, we have a lot of binary numbers to keep track of, like a lot. For example, cryptographic keys. If you're ever doing something to secure something, you want to have very long cryptographic keys. It makes it harder for attackers. You might have 256 bits in your cryptographic key. If I had to read you 256 bits individually, that would suck, right? Long numbers are easy for the computer, but they're hard for people. If I had to go through a list of 256 digits and go 001110, 01, 0111, 001010110000, it would get exceptionally boring. We would get lost. We would make a mistake. That would suck, right? Programmers are lazy. They don't want to do things that suck as much as they can. So we have something else that we use. For long series of digits, we have what are called hexadecimal numbers, or just hex. So for long series of binary digits, we represent them in hex. Hexadecimal is actually base 16. It uses 6 characters, 0 through 9, which we are used to, and A to F, which we are typically not used to using for numbers. If you add all the characters between 0 and 9, A through F, how many do you get? 16, it's right there on the board, okay? So this is base 16. When we're using base 16, each one of these characters, 0 through 9, A through F, represents one nibble. Do you remember nibbles, the things you thought I was joking about before? How many bits in a nibble? 4 bits in a nibble. Each one of these hexadecimal numbers is one nibble. And there is a table of all of these nibbles. Don't write this down right now, okay? You can look at it later. But essentially 0 is all zeros, 1 is 0, 0, 0, 1, 0, 0, 1, 0. I will show you very quickly how to build this table, okay? Eventually you will mostly have it memorized. If you were a computer geek, I know most of these from memory, but here's, when I need to draw the table, here is how I do it. The leftmost column, zeros and ones alternate. So you do 0, 1, 0, 1, 0, 1. Right? I'm not going to draw the whole thing. The second column over, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1. Right? So this one is 1, 0, 1, 0. The second column is 2 zeros and 2 ones. What's the third column? 4 zeros and then 4 ones. What's the last column? 8 zeros and 8 ones. Okay? So if you need to draw this table, like, I don't know, maybe during a midterm exam, hint, right? This is how you draw the table. The rightmost column is 0, 1, 0, 1, 0, 1. The second column is 2 zeros, 2 ones. Third column is 4 zeros, 4 ones. And remember, this is 2 to the 0, 2 to the first, 2 to the second, or 1, 2, 4, 8. If you can remember those columns, that's how many zeros you write in that column. And then once you've filled everything out till you get 4 ones, you fill in 0 through 9, A through F, and you have the hexadecimal table. Seems simple enough? Okay. The other way you can remember it is that 9 in binary is 8 and 1, and so we have an 8 in the column. A is 10, B is 11, so you have 8 and 2 is 10 plus 1. F is 15, so it's 8 plus 4 plus 2 plus 1. It's the same way. They're all the same thing. But the easy way to remember it is when you have to draw the table, do that alternating thing. So here's what we do. Given a very long binary number, and that one, by the way, is not very long. That's a relatively short one right there. Given a long binary number, it is much easier to split this number into nibbles. So here I've split them into nibbles. And then you replace, oh, sorry, let me go back a little bit if I can. Okay, here's our long binary number. And if you actually look, this one is even in numbers of 4. Most binary numbers are even in numbers of 8. I'm going to break my leg during this class. You know, I'm going to put that chair there. So when I fall, I'll fall on the chair. All right. Split it into nibbles. I did it vertically in this slide, but you don't have to. You can literally just like go through and figure out where the nibbles are, and then replace each nibble with the correct code. Yep. You would start from the right and go back, just in case the number was like not even. In computer world, there will always be even. Like there'll actually always be bytes. And you might have some leading zeros at the front, and you can just make all those zeros. So for example, that long binary number, we have now split into these nibbles, and then we write the number like this, DAC 78E7B. That is way better than 1101, 1001, right? Like having to read out all the binary. Now, oftentimes when you do this, what you do is you put 0x in front of it. If you ever see a number that has 0x put in front of it, that means it is a hexadecimal number. Okay. 0x is commonly used to indicate. Now, all right, everybody good with this? You'll have a little practice on this in just a minute, okay? Now, the other notations, sometimes what will happen, particularly in textbooks, is when we're talking about a number, the base will be indicated as a subscript. The base will be indicated as a subscript. The reason you need this is because it is entirely possible to have the same number in different bases that mean different things. So for example, in base 2, 101 is 5. In base 10, 101 is 101. And if you did the conversion between base 16, this would be 16, 16 squared, 16 cubed, you would get 256. So without the subscript, it's not clear what base you're talking about. All right, who's still with me? Who's against me? Okay. Good. All right, well, let's do some exercise. So remember the other class we talked about doing partner solving problems? I'm going to take little breaks in class every once in a while, and we will do some partner solving problems. I meant to do some at the end of last class, and we didn't get the time, so the first thing we're going to hand out are some exercises on flowcharting. We will not do these in class, but I like to give them to you anyway, and the reason is because now if I give you some of these, then the midterm will not be as surprising, right? Because if I'm writing all these problems, you will have practice problems in class, and then one day you will take a midterm and final, and you will have practice on a whole bunch of things that I've already done. Now, I would just ask you, if you're sitting in on the class and auditing, I'm going to try and make enough copies for you of those. But if there's not, I'd like you to pass them on to the students who are actually enrolled, if that's fair, okay? I tried to print enough. Let me know if there's enough. So the ones I just handed out, are simply for your reference. I would do those some other time on your own. I'm about to hand out another one that has binary conversion. Please find a partner. And what I would like you to do is, well, I'll tell you in a second. Let me hand these out, and I'll tell you what we're going to do. Yeah. Nope. But if you want to do the answers, I don't have the answers. I don't hand them out. Most of the time, we'll do them in class, and so you'll see the answers. Those I just didn't get to because we're running a little behind. If you want to come to my office hours or talk to the TA, you can do that. All right, so right now the thing we're going to do is partner up. We're going to do partner exercises. Start with the front that says convert 93 base 10 to binary. One of you do that, and then your partner does the other one. When you're done, wave at me, okay? All right, how we doing? People finish the first sheet, the first two problems? Show of hands if you finished the first two problems. All right, I'm going to give you another 30 seconds, and we'll have someone come up and do the answer for us. Wait, did you all flip to the back sheet already? All right, let's do the first two. So, stop, pause, halt. How are we going to do this? 93 base 10 to binary. Who wants to help me with this? Yes? We're going to start with 128. Does that fit into 93? It doesn't, so we have 0 of those. Next number is 64. Does 64 fit into 93? So if we subtract that, we get 29, right? Next number is 32. 29 doesn't fit into 32? Nope, you're right, it doesn't, right? So I'm sorry, 32 doesn't fit into 29. Okay, so the next number is, does 16 fit into 29? How many times? Once. So now we have 13 left. Okay, next number is down is 8. Does 8 fit into 13? It does. Fits once. So we have 5 left. Next number down is 4. Does 4 fit into 5? It does, so it's one of those. We have 1 left. Next number down is 2. Does 2 fit into 1? It does not. We have 1. Does 1 fit into 1? It does. So our final number is going to be 1110. 0010. That's how I would write it, right? We have 1, 2, 3, 4, 5, 6, 7, 8 digits. I like to write them so that we have 8 digits. 8 binary digits is a... The answer is, the way I would write the answer is 00101101. Is that wrong? Did I do it wrong? Oh, you're right. Sorry about that. Yes, sorry, 101. I reversed the bits. Sorry. Here. By the way, there's a prize in the class for catching me in a mistake. There's your prize. So, sorry about that. So, I wrote that down incorrectly. The correct... So, 01011101. If you omitted the first 0, that's fine. Who's baffled now? Who's confused? I can tell by your faces that you're confused because you look confused. So go ahead and raise your hand. Yeah. Yeah, and if we add it back up, we would have 1, 4, 8, 16, 32. If we added all these up, these two make 40, these two make 20, that makes 1. So wait a minute, something went horribly wrong. 64, sorry. Until today you thought I knew what I was doing, didn't you? So. But if we add these two up, 64 and this are 80, plus 12 plus 1 is 93. You with me on that? Okay. I'm sorry I made that mistake. I know I'm baffled. Okay, how about the other one? What's the next question? Yeah. All right, so 0, 1, 1, 0, 0, 1, 0, 1. Did I write that out right? 0, 1, 1, 0, 0, 1, 0, 1.
What I did was, if there was a 1, I wrote it out just like that with the numbers above it. And if
Yep.
there was a 1, I took the number above it and I just
Yep.
wrote those down and added them.
So this is 64 plus 32 plus 4 plus 1, which is what? 101. So 4 plus 2, 8, 10, 11, carry the 1, 9, 10, 101. Everybody good with this? All right, go ahead and do the other side now. Faster though, faster. Are you all done with this one already? You all so quiet. How many of you all are done with this one already? How many are not? Oh, okay. I'll have 1 minute, so. All right, who's ready to do this one? Yeah. All right. Yeah, this is why we use hex, right? Because it kind of says. So 2AE, we can just write this out without even looking at the table because we know the table 0010. A is 10, 00, sorry, 10. E is 110. There we go. We're done, right? That's pretty easy. This one we split into 4s. I kind of spaced it out a little bit here. And most of these I can do off the top of my head. This one's 11, so it's B. This one's 6. This one, oh, wait, 2, 4. Yep, this one is 4. This one's 3. This one's, what's the last one there? I'm going to cheat and look it up. E. So, right, just, thank you. So, these you can just look up. Right. And then when you do this a lot, you'll have memorized. All right, everybody good with these? Everybody see the use of like not having to say 00, 10, 10, 10, 1110 and able to say 2AE instead, right? Okay, that's why we do that. Okay, so let's get back to what we were doing. So computers all work off of binary numbers. This is our model of the computer that we were talking about. We have, sorry, I'll give you like 30 seconds to get back to note-taking mode. Do you like doing the exercises in class, by the way? Yeah, they break it up, they help, and then you get sample things for the exam, which is good. All right, so back to the computer. Here's what we had. We had CPU that does what? One word. We have RAM that does what? 2 words. Remembers stuff. We have disk that does what? Remembers things even when there's no electricity. We have the monitor, which is what? It's for us, and we have keyboard, which is what? Input and output, right? So that's everything we have. So let's talk about how the CPU works, okay? Computers are what? But they're dumb, very, very, very fast. The CPU is the heart of the computer. It does all the math. The CPU is dumb, but it's dumb very, very, very fast. So here are the dumb things that a CPU can do. The CPU can go and it can get a number from RAM. It does so because the number takes the bus to get there. It can get another number from RAM. Again, it uses the bus. It can perform some operation on those numbers, like adding them or subtracting them, multiplication, division, whatever. And when it's done, it can put the result back in memory. That's essentially what the CPU does. And it does it very, very, very fast. Now, this putting the result back in memory is sort of important because it doesn't always do much good to do an operation. But you can omit it if you want. The CPU can just get numbers from memory and do something with them, and then just forget about the results if it wants. We'll sort of see that later. It's not common, but it sort of happens. Okay. That's all the CPU does. It gets number from RAM, does something, puts some result back. But very, 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 very fast. RAM has its own structure. So RAM is memory, and RAM looks like this. RAM is a 64-bit word. Remember that we talked about the computer works in fixed size chunks because it's easier to design the circuitry to operate in fixed size chunks. So the memory is aligned in words, and it has a lot of these things. Millions or billions of these things. Every one of these things is like a memory cell. I'm just going to call it a box because that's all we have to worry about. Every one of these boxes has an address. The address essentially is just the number where it is, whether it's the first box, second box, third box, fourth box, whatever. Okay? So we have all these boxes. They happen to be the size of the CPU. They have addresses, which later in the semester you're going to see are hexadecimal numbers. Why are they hexadecimal numbers? Because they're huge numbers and they have lots and lots of bits. So later in the semester, you're going to see that we're going to have a 64-bit word. 64 bits is 8 bytes. 8 bytes is 16 nibbles. Each nibble is 1 hexadecimal character. So later in the semester, you will encounter memory addresses that are 16 hexadecimal characters. And when you see those, something will have gone very wrong in your program. Okay? But I want you to understand they're there. So RAM. It has words, it has boxes. The boxes are numbered from 0 up to some very, very, very large number. Each time the CPU accesses some memory, it is accessing one of these boxes. Every time it accesses. Okay. Everybody good with that? That is how memory works. Disk, we will talk about later. All you need to know is that we can send data to and get data from the disk if we want. We don't really need to draw a picture of that. It's actually more complicated. So everybody good on how the computer works? CPU, what does it get memory from? What does it do with it? And what does it do after it's done with the operation? What is RAM structured like? A bunch of boxes. How many? Billions. And they are numbered from 0 to some billions. What kind of number do we associate with the address? Hexadecimal. Okay, good. All right, that's all you need to know. We've talked about algorithms. We've talked about the structure of the computer. You know what we can start talking about? C++ code. So let's look at C++ code. And what we're going to do is we're going to talk through C++ code that looks just like the first algorithm we saw, okay? And we will compare the two. So you remember yesterday we talked about this algorithm. What does this algorithm do? Tells you if a number is odd or even. Now earlier today I had a question about how to use the decision, right, for the homework. If you want to use a structure like this, that's fine. Decide, is something true or false? If so, do something, otherwise, or if not, do something else. Okay? Does that make sense? You can use a structure like this for the homework if you want to. But something like that makes sense. So let's look at this. We start our algorithm. We input and say, tell me a number. So the user knows what they're being asked for. We divide that number by 2, and we decide to say, after we've divided that number by 2, is the remainder 1 or not? If it is 1, then the number is clearly even, right? Of course not. Okay, the number is odd. I'm just checking to see if you're paying attention. And if the remainder is 0, then the number is clearly prime, right? Even. Come on, fix me up here, guys. So. All right, everybody with me? And then we stop the algorithm. Everybody good with that? All right, here is the same algorithm expressed in C++. And I'm just going to talk you through this piece by piece, okay? So this code I will put up someplace you can find it, so you don't have to write it all down now. You'll be able to see this in the video lecture. If you go back and look at it, you'll have a lot more chances to see C++ code, so don't worry about writing this down right now. Okay, this is not an exercise in copying, it's an exercise in thinking. So here we have pound include IOStream in brackets using namespace std. That doesn't stand for what you might think it stands for. It stands for standard. So int main parenthesis bracket int input equals 0, int remainder equals 0, cin angle input, remainder equals input parentheses 2, I'm sorry, not parentheses, percent 2. If remainder equals 0, cout even indel, else cout odd indel, return 0. That is the same algorithm expressed as a C++ program. So let's figure out which parts of that correspond to the algorithm that we saw like this. Okay. What is the first step in our algorithm? Start. Start. What? Yeah, start. Well, that's the first step of your projects, is to start early. So this algorithm, we just start. In C++, for this purposes of this class, for most of the semester, these 3 lines indicate start. Pound include angle bracket IOStream, close angle bracket, using namespace standard, abbreviated std, semicolon, int main, open close parentheses, open curly brackets. That part together means start. Now, I can tell you some of the stuff is magic. I will tell you these 2 lines up here at the top. Remember I told you programmers are lazy. They don't like to recreate code. They like to use code other people wrote. These 2 lines give us access to code other people have written for us that allows us to do input and output easily. Okay? That's that magic part. Okay? And int main, open close parentheses, open bracket, is part of start. So every time you have a program in this class for the first part of the semester, you will use this for start. Got it? Everybody good on that? These things are magic and let you use other code. This tells the program where to start. Every time your program runs, it will look for this int main, and it will start right at that int main. Every single time. On occasion, I get paid really disgusting amounts of money to be part of a patent case, and they dump a whole bunch of code on me, like for a commercial product, and it takes me typically a while to figure out where this int main is. And when I start looking through huge amounts of code, I almost always try and figure out where the int main is so I can start reading code from there. Okay, yes, sir. When I get huge amounts of code, it's typically like hundreds or thousands of files split up and stuff is across each other, and I use some special tools to process the code. The other thing is oftentimes when I get a dump of code like that, there'll be like 10 different versions. So I have to figure out which version, and then there'll be like test code that has their own main part, stuff like that. So it gets complicated. Yeah. Okay. Sorry, I shouldn't have said anything. You will never have any problem finding int main. Because when you do this, you will have one file. You will have only int main. When I do this consulting stuff, I'm like, I'm very minor wizard with code, and there are people who are way better than me, but I know enough to like be able to look through large code bases and figure out where the program actually starts, because it's not always apparent with lots of code. For your projects, it will always be easy. You will always find int main, open close, parentheses, curly bracket. Everybody good? I don't expect you to like go out and review code for money after this. That would be insane. Okay, so all this is start. All of that together is start. Okay, at the end of the program, we have stop. Right? Start. If you start, you have to stop. This line right here, this return 0, and this closing curly bracket, which is the matching partner to this one up there, all of this stuff inside is in between these two curly brackets, including the return 0, means stop. Yep. We don't have any semicolons yet. We've talked about start with no semicolons. We've talked about stop, but we do have to have a semicolon after return 0. So in general, that's the punctuation that ends a C++ statement, is a semicolon. Okay. Who's still with me? So we had start, pound include iostream using int main. We have stop, return 0, curly bracket. So just like that, just stop. Okay, everybody good still? As an aside, we now are able to write the shortest possible C++ program. Right? It would look like this. Pound include iostream using namespace standard, int main, open close parentheses, open curly brackets, return 0, close curly brackets. That is a program that executes the algorithm start and stop. Does this program do anything useful? No. But if you were to type that into the computer, and we'll talk about this next class, the actual process of editing and compiling code, that would give you a program that would run and do nothing. Is it useful to have a program that does nothing? Oddly enough, it is. What do you think your computer is doing when you're not using it and it's just sitting there being bored? On Microsoft Windows, there is literally a program that does nothing, and it's called the idle task, and it just starts and stops. Now, it's a little more complicated than that. I'm lying to you, but conceptually, that's what it does. Okay? So, congratulations. You now know how to write C++ code that does nothing. It's a start. It's a start, though, right? So, yes, it's also okay. Input. Tell me a number. Okay. Input. Tell me a number. When we're doing input in C++, we can't just say input. We have to do something a little bit more. And what we have to do is we have to say where the input is going to go. Remember, the CPU can get a number from memory, it can do some operation, and it can put a number back into memory. When we are writing our programs, we have to specify which memory boxes we are using and what their values are. So before we actually can do input, like we just talked about, we have to do something that isn't in our simplified algorithm. And the thing that we have to do is called variable declaration. Variable declaration. The idea behind this is that we have to tell the computer how we are going to use the memory, right? I showed you memory. It's a whole bunch of boxes, billions and billions of them. We have to specify what the boxes are, okay? And in particular, what we're doing is we are telling the computer to choose a spot in RAM that is currently not being used to store some value. Does that make sense? So, since the CPU can get a number from memory, it can put it back, we have to manage the memory ourselves. We have to take care of where things are getting put. So here's what we do. In general, when we have variable declarations, and we'll go over this in more detail later, what you have to have is a name, which is the name for the box that you're going to be using, How many of you all remember names better than numbers? So if we're able to take a memory box and instead of saying it's at address 0AX, 0AF3279, right, that sucks. But if I tell you it's at the address called input, or it's address called remainder, right? If we give it a name instead of a number, we like that better. So when we declare a variable, we have to have a name, which is useful to people to understand what is being stored at that spot. We have to have a type, and a type means, as we'll see later, like whether it's a number, whether it's an integer number or a floating point number, whether it's letters or something like that, because everything is binary, everything's encoded in binary, and you have to know which encoding you're using. Okay, so we have a name for people, a type so that the computers are doing, and if we want to give it some value, we use the equal sign. And the equal sign stores that value in that little memory box. So here's a picture of what's going on. We're going to need two memory boxes to hold things. We're going to need one called input, and that's going to hold the number that the user types into the computer. We're going to have one that's called remainder, and this is going to hold the remainder of the division. Now, when these lines of code execute in C++, here's literally what happens. The computer goes into RAM, and it finds some memory somewhere out of all the billions of cells that we have, and it assigns a label. One of them gets labeled input, and the computer remembers that this is an int for an integer, not a floating point number, but an integer that is just solid units with no fractions. Okay? And it says input, this box right here is going to have the name input, and by the way, when you get something out of there, don't forget it's an integer. It's not something else. And it's going to say we're going to have a box named remainder. It's actually going to be put right next to input because why not? We're already right there. It has the name remainder. It has this integer type. And by the way, we have these equal signs. Put some zeros in there just to get started. Yeah? Okay. So the question is, do you have to assign a value as soon as you declare it? And the answer is no, you do not. But the real answer is yes, you do. Because here's what happens. When the computer goes and grabs one of those memory boxes, it might not be empty. And if you don't tell it what to put in there, and you don't initialize it, the next time you look in that box, you're going to get a number that might be quite surprising to you. Because the thing that's in there might not actually be a number. It might not be an integer. It might be some text. It might be something else. And the computer's going to look at it and go, oh, look, I have a whole bunch of bits in here that I think is an int because that's what it told me. But now I'm going to try and assume that thing's an integer, and bad stuff will happen. Bad things will happen. And in fact, for the first number of projects, forgetting to assign these things is probably the worst thing that can happen to you. Because what will happen is you will run your program, and it will output weird stuff. It will output apparently random numbers, and you'll be like, wow, what happened? Okay? And trust me, it happens to everybody. I mean, I still forget occasionally to assign variables, and then it's a disaster. Okay? So the answer is you don't have to put this equal there at 0 if you don't want to, but you would be insane not to. Okay? All right, let me just see. Let me just finish up. Okay, so why do we have the type? Right, I think I kind of explained this. Why do we have that int there? Everything is just a lot of ones and zeros. The computer is a tool. It can pump ones and zeros through it very fast. So you have to know, you have to encode whatever data you have in ones and zeros. The way you encode integer numbers is very different than the way that you encode letters and other numbers. Okay? And this is where we will start when we come back on Wednesday. So, see y'all later. Have a good homework.